in this lecture I will be looking at Fourier expansions a little more. We will look at Fourier expansion of some simple functions just to show you how it works, and then we will show how we use Fourier series to write differential equations in simpler forms, and in some cases you can actually solve them. So, first let's before we get started, let's write the Fourier series in a slightly different form. Okay. This is also a form that is very common. Okay. So, we wrote our Fourier series as a0 by 2 plus sum over n equal to 1 to infinity a n cosine n pi x by L plus b n sin n pi x by L. Okay. There is an alternate form of the Fourier series, okay, which is to write from it as f of x is equal to sum over n equal to minus infinity to plus infinity c n e to the I times n pi x by L. This is exponential of an imaginary number. Okay. So, you know that e to the I times 2 pi is equal to 1. Okay. So, we use this result, okay, e to the I times 2 pi is 1, okay, and you take any power of this. So, if you multiply this by any integer, then you will get 1. So, this implies that e to the I times 2 pi n is equal to 1 for when I say n equal to minus infinity to plus infinity, this is for any integer n equal to 0, plus minus 1, plus minus 2 and so on. Okay. So, this is the alternate form of the Fourier series, okay, and when you write the Fourier series in this form, okay, then our C j, okay, and this you can verify, okay, can be shown to be equal to 1 over 2 L integral minus L to L, then you have f of x e to the I into j pi x by L. Okay. Now, this j is an integer, okay, j is an integer which is a coefficient, I is the imaginary exponent, okay, this times dx. Okay. So, this is the alternate form of the Fourier series, and very often this is used. Okay. In fact the in quantum mechanics, okay, this function e to the I pi x by L times n is referred to as a plane wave in so this is often referred to as a plane wave. Okay. And okay, and this is this writing this f of x in this form is often referred to as a plane wave expansion. Okay. So, this is about Fourier series, okay, in a different form. Now, a few other things I want to mention about Fourier series. Now, let's take some examples. So, f of x is equal to, let me write, equal to x square. Okay. So, suppose f of x equal to x square. Now obviously, if you have a simple function like x square, your Fourier series is not really important. Okay. But nevertheless, we will take this function just to illustrate the calculation of your Fourier coefficients. So, then what you will say is that a j is equal to integral 1 over L integral minus L to L. Okay. So, and again I will take the interval. Okay, let me take the interval from minus 1 to 1. Okay, I am choosing my interval as minus 1 to 1. Okay. So, then this becomes 1 over 2, and now I get x square cosine. Now, I will get j pi x, L is 1, dx. Okay. So, now what do we, so can you do this integral? Okay. So, the question is, can you do this integral? Okay. Now, can you do this for an arbitrary value of j? Okay. Now, if you want to do for an arbitrary value of j, what you will say is that you will integrate this by parts. So, so the first term will be x square, integral of cosine is sine j pi x divided by j pi, okay, and this whole thing is from minus 1 to 1, and the other term is minus. Okay, now, what you have is integral of derivative of x square is 2 x times sine j pi dx from minus 1 to 1. Okay. Now, when x equal to plus 1, then you have sine j pi. Okay. So, so x equal to 1, then you have 1 times sine j pi, and when x equal to minus 1, again you have 1, and you have what you have is plus sine of you, or rather you have minus sine of minus j pi divided by j pi. Now, sine j pi, if j is an integer, sine j pi is 0. Okay. So, this whole thing is 0, this whole term. So, each of these terms is 0. Okay. Now, the second term, okay, now you still have let me cancel the 2's. Okay. So, I have minus, now I have integral of x. So, I have 1 by j pi, I will take it outside, and I have integral minus 1 to 1 x sine j pi x dx. Okay. So, now so what I will get is 0, and here I will get minus 1 by j pi. Okay. Now, again I will do the integration by parts. So, the first term is x, integral of sine is minus cosine j pi x divided by j pi. This whole thing is evaluated from minus 1 to 1, and then you have minus integral of, now what I will have is derivative of x is 1, and I will have a cos j pi x 1 dx. Okay. So, so now what I can write this as, okay, I can write this as, now let me take j pi and j pi. So, I have 1 over j pi the whole square, and what I have now, when x equal to 1, then I have minus cosine of j pi. Okay. So, what I have is minus cosine of j pi. When the x is minus 1, then again I have minus cosine of j pi. So, and then I have a minus sign here. So, I can write this as 2 cosine of j pi. Okay. I'll leave it as cosine of j pi for now. Okay. We'll look at it a little more closely in a bit. Now the other term. Okay. So, I have in this case I have minus 1 by j pi square, and I have integral of cos j pi. So, what I will write it as, I will write it as minus 1 by j pi cube. Now, integral of cosine, I have a sine j pi x from minus 1 to 1. Okay. And now, what I will get is 2 cosine of j pi divided by j pi square minus, now sin j pi x of course will go to 0. Okay. Sin j pi and sin minus j pi are 0. So, we will just get this. Okay. Now, what is this equal to? So, cosine of j pi, cosine of pi is minus 1, okay, cosine of 3. So, if you look at your cosine function, okay, this is pi, 2 pi, 3 pi. So, cosine of 0 is so it goes something like this. So, this is basically you can easily show that this is 2 minus 1 raised to j divided by j pi. Okay, so, cosine of j pi is minus 1 raised to j. Okay. So, basically you get a j equal to this, and you can easily show that b j has to be 0. Okay, and why does b j have to be 0? Because our choice of function x square is an even function. You can easily verify by actually doing the integral. Okay. So, therefore, I can write x square is equal to sum over j equal to 0 to okay, what about a 0? So, a 0 if you put j equal to 0, then you get minus 1 raised to 0, that is 1. Okay. Okay. In this case, you cannot do this for this is j not equal to 0. So, this is true for j is not equal to 0. Okay. Now, if j equal to 0, then you can see this that if j equal to 0, then a 0 goes to 0. Okay. You can see this by looking at this. Okay. So, a 0 is equal to cosine of x square. Or okay, let's evaluate. A 0 is equal to 1 over 2 integral minus 1 to 1. Now, what I have is x square. Now, cosine of 0 dx, cosine of 0 is 1. So, this is 1 over 2. Now, what you have is x cube by 3 from minus 1 to 1. Okay. So, this is 2 by 3. So, this is equal to 1 by 3. So, a 0 is equal to 1 by 3. Okay. So, I can write x square, I can expand it as, now a 0 by 2 is 1 by 6 plus sum over let me just write it as n equal to 0 n equal to 1 to infinity. Now, a j is 2 minus 1 raised to j divided by j pi, and then you have cosine of j pi x. N, and replace j by n. Okay. So, this is the expansion of x square. Okay. So, what you did was you are writing x square, okay, as a sum of x square in terms of periodic functions. Okay. Again we wrote x square from minus 1 to 1. Okay. What the implicit assumption, okay, is that what we are doing is we are imposing periodicity. So, when I write x square, so if this is minus 1 to 1, x square looks like this. When you impose the periodicity, okay, then what we are going to say is that this same function keeps repeating. So, it goes like this. So, what we are really looking at is a function that looks like this. Okay. And when you expand this as in terms of sines and cosines, then only the cosine term appears, okay, and it appears in this form. Okay. So this is a very nice illustration of the method of Fourier series. Okay. Another example which I want to emphasize. Okay. So, suppose you have a discontinuous function. Incidentally, what I would encourage each of you to do is to actually take the first term. Okay. So put n equal to 1, calculate cos pi x, okay, and try to plot by taking finite number of terms. So, take n equal to 1, then take n equal to 1 and 2, 1, 2, 3. So take more and more terms and see, and you can actually see how this infinite series will converge to f of will converge to this x square function. Okay. So, that is an interesting exercise that I encourage all of you to do. Okay. Now, coming back, let us take an example of a discontinuous function. So you can take f of x is equal to 1 for x greater than 0, equal to minus 1 for x less than 0, and L equal to 1. Okay. So, now again I can do the Fourier expansion. Okay. So in this case you can clearly see that f of x is an odd function. Okay. So, a n of x a n equal to 0. Okay. So, there are no cosine terms. So, f of x is equal to sum over n equal to 1 to infinity b n sin n pi x, okay, L is 1, okay, where b n is equal to integral minus to 1, okay, 1 by 2, okay, and what I have is f of x sin, let me say b j sin j pi x dx. Okay. And now, if I can do this integral in two ways. So, first I do from minus 1 to 0. So, I get half integral minus 1 to 0. Now, from minus 1 to 0, okay, f of x is minus 1. So, I have minus sin j pi x dx, okay, and then plus half integral 0 to 1 sin of j pi x dx. Okay. Now, now what is this integral? Integral of minus sign is nothing but plus cosine. So, so I can write half cos j pi x by j pi from minus 1 to 0 plus, or I can write minus half cos j pi x by j pi from 0 to 1. Okay, these are the two terms, and you can easily verify that when x equal to 0, cosine of 0 is 1. Okay, so you get cosine of 0 is 1 by j pi. So let me take the 1 by 2 j pi outside. Okay. Now, so I will get cosine of 0 minus, now I have cosine of j pi into minus 1, cosine of minus j pi, which is nothing but cosine of j pi. Here I have minus cosine of j pi. Okay. The first term will be cosine of j pi, I have had a minus sign outside, and I have plus cosine of 0. Okay. So, I can write as 1 over j pi, cosine of 0 is 1, okay, and cosine of j pi is minus 1 raised to j. Okay. So, this is my Fourier series. So, I know my terms. Okay. You can check B 1 is equal to 1 by pi 1 minus 1 raised to 1 is minus 1. So, 1 plus 1, that is 2. So, B 1 equal to 2 by pi B 2 equal to 0, B 3 is equal to, so again I get 2 divided by 3 pi, okay, and so on. So, basically I can write f of x is equal to 2 by pi, okay, sine pi x plus sine 3 pi x by 3 plus sine 5 pi x by 5, yeah, so on. So on. Okay. So, this is my f of x. Okay. So, this is how you expand a function that is not continuous. Okay. Now,